Welcome to the UEI Technical Masterclass. I'm Bob Finn with UEI, and I hope everyone here is doing well. Today's webinar is entitled Accelerating Product Development with UEI Automotive Solutions. Our presenter will be our own Prabhu Radhakrishnan. In this masterclass, Prabhu will be providing an overview of the different UEI solutions that can be applied to automotive industry applications. As always, I want to remind all our webinar attendees this is an interactive environment, and we encourage all of you to ask questions. So if you do have a question, send it our way using the webinar chat tool. And I think that about wraps up my brief introduction. So without further ado, I'm going to hand this over to you, Prabhu.
So today's webinar topic is accelerating product development using UEI's automotive solutions. So the main objective of today's webinar is to give an insight on how the UEI's products can be adapted for use in automotive applications. So though UEI's products are well known for their application in the aerospace, defense, and space industries, the products are also equally well suited for use in automotive product development applications. So let's take a look at today's agenda. So we will have a quick introduction to the UEI's product platform. Then we will move on to a selection of automotive applications that I would like to cover. The first one being dyno testing and UEI's EtherCAT solution, or using EtherCAT technology. Then we will move on to take a look at hardware in the loop testing applications. And also finally, we would be looking at in-vehicle data logging solutions. So we'll be having a question session in between, and also we'll have some time for taking further questions towards the end of the session. So to give a quick introduction, so UEI offers rugged and flexible I/O data acquisition systems. So our PowerDNA distributed network automation chassis are basically Ethernet-based data acquisition systems, which could be used for data acquisition and control applications. So each chassis includes a CPU, a real-time operating system, and an Ethernet interface, and a different number of slots depending on the type of device, which allows installation of various I/O boards. So there are about 80 different choices of I/O boards that you could choose from to populate into these slots. So the picture here shows the family of the UEI devices. On the left, we call them the cubes, or the DNA chassis. So these are compact chassis, ideal for laboratory and in-vehicle applications. So we also have a military spec version of the cube for IP rated, for applications which requires IP rating. Then on the right, we have the rack chassis. So we have a 12-slot full rack, a 6-slot half rack, and a 4-slot flat rack. So the number of slots denoting the number of I/O boards that you could populate in there. And also we have the military versions of the 12-slot and the 6-slot chassis for IP rating. So I would like to point out some key features that makes these chassis ideal for automotive applications. So the first point is these devices are extremely rugged for use in harsh environments, let it be dyno test cell environment where it's high electrical noise, or let it be used in-vehicle applications. So all these devices are tested for 5G shock and 100G vibration, so it makes it ideal for working in these harsh environments. And then we have a wide variety of I/O boards, like CAN boards, analog I/O, digital I/O, thermocouple temperature measurements, etc. So for any type of signal measurements, there are these I/O boards options available. Then these devices are capable of operating in the industrial operating range in terms of temperature from -40°C to +85°C. And also these devices support multiple operation modes. So we can have these devices work in standalone mode. We can have these devices work as a slave device plugged into an host PC. So depending on the type of application, you can select the operation mode, making the platform very flexible. And another advantage is the 10 years availability guarantee on all these products. So the 10 years availability guarantee is from the day we call end of line for these products. So from the date we call end of line, the products will still be available for 10 further years. So the obsolescence issues are being handled by us. So now we will move on to looking at the automotive applications itself. So first application is we'll be looking at dyno test setup using EtherCAT technology. So we'll have a quick look at what EtherCAT technology is, the functional principle of it, and also the UEI's EtherCAT options and how the hardware can be used. Then we will move on to look at hardware in the loop testing and how the UEI hardware slots into an hill testing setup. And finally, we'll be looking at in-vehicle data logging, and also we have a sample application that's already deployed in the field. So first, let's take a look at an introduction to EtherCAT. So EtherCAT is in real-time industrial Ethernet technology. It was originally developed by Beckhoff Automation, and it was introduced in April 2003. So the technology has been standardized and maintained by EtherCAT Technology Group, or ETG, they call it, since November of 2003. So some of the main advantage of using EtherCAT technology is mainly focuses on shorter cycle time. So because of the nature of the protocol, so we are able to achieve very short cycle times of less than 50 microseconds. And also, the technology offers low jitter for very accurate data synchronization. And because of the standardized nature of the protocol itself, so the hardware costs are much lower. And in terms of topology, technology is very, very flexible. So there is no restrictions on the type of topology that you need to have in your system. And also it offers full duplex feature. So because of the advantages of that EtherCAT technology offers, it makes it an ideal candidate for using it as a central backbone within a dyno environment. So we'll go into further details about the functional principle of EtherCAT itself. So each EtherCAT network consists of two main components. The first one being an EtherCAT master, and then we can have up to 254 EtherCAT slave devices in the network. So the master sends a telegram that contains the data packets that passes through each slave node. So these telegrams, EtherCAT data packets, are just UDP packets. What differentiate them from regular UDP packets is the addressing scheme. So the addressing scheme for EtherCAT packets is different from a standard UDP packet. So the EtherCAT packages are not really compatible with a regular Ethernet network, but the structure is kind of very similar to how an UDP packet would look like. So once the master sends telegram out, so each slave device on the branch reads the data that is addressed to that device and then inserts whatever data it needs to put back onto the bus downstream on the fly. So because of this nature is what makes EtherCAT very effective, because there is no separate data stream that is addressed for each device. There is one single data stream, and the data inside holds the addressing information that refers to each device, slave device on the network. So once the data reaches the last node in the segment, it detects an open port, and that node would be sending the message back to the master. So that's how basically the technology works. So we'll take a look at a quick graphic which shows this exact principle and how it works. So as we can see in this network, we have a master device, and here we have around 6 slave devices. So the master is now sending the telegram out. We can see as the data passes through the slave devices picks up the data, whatever is addressed to it. And then when the data is going downstream, it offloads the data that needs to be put back onto the bus. So the telegram is passing through every device on the network. And once it reaches the last device, it is sent back to the master. So this process is continued again and again, and the data is just passing through all the slaves. So that's how that kind of explains the functional principle of EtherCAT itself. So we have a wide variety of EtherCAT options. So we have all our I/O devices are compatible as EtherCAT slave devices. So we have our DNA ECAT series of devices, which is our EtherCAT slave device. It's compatible with both our Power DNA and DNR product line. So the picture here shows the Cube chassis, but it is also compatible across our rack chassis as well. So the only difference between this and a standard cube or a rack is the CPU layer. So the I/O layers are exactly the same across a standard cube and an EtherCAT cube. So we just have a different CPU layer to accommodate the EtherCAT communication. So we have our own specific vendor ID, and along with these devices, the slave information files would be provided, which are required to be imported into the master software so that these devices can be detected by the master. So I would like to play a quick video which shows our EtherCAT solution and how it could be used and how to set it up.
We've built a UEI EtherCAT system with maximum flexibility in mind. Among the features it includes are a new CPU module, specifically designed to run as an EtherCAT slave, high-density channel counts, compact, rugged construction, compatibility with a wide array of I/O options, and the ability to configure the system with an EtherCAT master. That means that whatever your application requires, we have you covered. Let's take a look at how easy it is to set up and configure. For this demonstration, we're using TwinCAT as our development environment. From this interface, you're presented with a directory list showing the connected UEI EtherCAT chassis and all the installed I/O boards. As you can see, our first board, the AI207, is an analog data acquisition board we're using as our input. We're outputting the signal through this AO318 high-precision analog output board. And we've also installed a DIO404, which is a 24-channel digital I/O board. To simulate an analog input signal, which you can see here, we've connected channel 0 on the analog output board to channel 0 on the analog input board. Let's take a closer look at that input board. Among the configuration options available is the ability to adjust the input voltage through 12 different ranges, from plus or minus 10 volts to plus or minus 12.5 millivolts. This flexibility makes it compatible with a wide range of sensors, even thermocouples. On our analog output board, you can adjust the output voltage from 10 volts to negative 10 volts. And we provide the ability to switch on and off any of the 8 channels. Additionally, this board is part of our popular Guardian series, which provides a powerful set of onboard diagnostics, such as monitoring voltage and current of each channel. These are features that let you quickly and easily diagnose short circuits, open circuits, and other possible failure conditions. Moving down to our digital board, through the TwinCAT interface, you can adjust the supply voltages, as well as modify the hysteresis of the supply voltages. This particular model can accept a wide range of input voltages, from 3.3 volts all the way up to 36 volts. Configuration options at this level allow you to customize your board to the voltage level of your system as needed. And all of these changes can be done on the fly, so you'll never need to shut down your EtherCAT system to make adjustments. As you can see, the UEI EtherCAT slave hardware provides unmatched configuration options. That versatility comes in a compact, rugged chassis that's built to withstand virtually any environment. And all UEI products are covered with a 3-year warranty and 10-year availability guarantee. So if you're looking for the most rugged, reliable, and flexible EtherCAT system for your application, UEI is here for you.
So that's basically the EtherCAT solutions. I see there are some questions that has come in, so we'll answer those questions before we move on to the next topics. So the first question is, can your device act as an EtherCAT master? Yeah, so on our UEI platform, so we have successfully managed to integrate an EtherCAT master library, which will allow you to operate our UEI pack hardware as an EtherCAT master. And we are also in sort of initial stages of defining a separate product, which would be a CPU layer that could act as a dedicated EtherCAT master layer. So, so please let us know if this is of interest, and I'll be happy to share more details offline. So the next question is, how does the master identify the EtherCAT device, slave devices? So, so as I mentioned earlier, along with the slave devices, we supply EtherCAT slave information files. So these files include all the information regarding our devices that are required by the master software to detect our hardware. So these files can be imported directly into the master software, so that when the UEI hardware is connected, the master software will detect the devices automatically. So we've got another question. Is it possible to use the EtherCAT hardware as a regular non-EtherCAT device? So, so even though the I/O layers between our PowerDNA hardware and EtherCAT devices are the same, as I mentioned, the CPU layers are different between the two. So, so you could swap the CPU layers and just change the faceplate of these devices. So to switch between an EtherCAT device to an PowerDNA device, or the other way around. Don't see any other questions at the moment, so I guess we can move on to the next topic. So the next topic is going to be hardware in the loop testing, and how the UEI hardware can slot into this into a hill testing setup. So this shows a basic block diagram of an hardware in the loop testing setup. A hill system basically includes an electrical emulation of sensors and actuator and a plant simulation model that runs on the host PC. So these emulations act as the interface between the plant model and the embedded system under test, which would be an ECU, it can be an engine control unit, transmission control unit, or an ABS unit, whichever unit is under test. So the value of each of these electrically emulated sensors is controlled by the plant simulation model, and it is read by the ECU. Likewise, the ECU implements its own control algorithms by outputting actuator control signals, and changes in these control signals is fed back to the simulation model, which makes decisions based on the signal that it received. So, so where does the UEI hardware slot in here? So exactly right in the middle, where it can act as the interface. So you can use the hardware to actually emulate these electrical signals for sensors and actuators, and this can interact directly with the plant simulation model. So you can use the for analog outputs, digital outputs, or even CAN channels or serial data. So you can simulate these data using the UEI boards, and feed that into the electronic control unit. And also you can use the I/O boards to read the outputs that is coming from the ECU and feed it back into the plant simulation for taking control actions. So so we have a full-on integration with Simulink for your model-based application development called the UEI Sim, which could be used to develop your plant simulation models as well, and interact with the hardware directly. So UEI Sim is kind of a separate topic on its own, so I'm not going to go into details today, but we would be having a separate webinar on just UEI Sim in the future. So this is how we could use the UEI hardware in a hardware in the loop test application. So moving on, so we'll be looking at in-vehicle data logging applications. So you can use the UEI Cube or the rack as an in-vehicle data logger. The Cube is more suited because of its compact nature of it, so it makes it ideal for applications where space is quite tight. So for example, we've got a 3-slot cube over here. So it is just 4 inches by 4 inches by 4 inches in dimensions. So makes it nice and compact. It's very easy to use. We have an intuitive Windows setup configuration application that you could use to configure the cubes and the I/O channels itself. For example, it has a high channel density. For example, in this particular cube, you can pack up to 150 analog inputs or around 288 digital inputs on just a 3-slot cube. So which makes the channel density quite high. And these devices are easily programmable via Ethernet. And also another advantage it offers for automotive application is basically the operating voltage of these devices are between 9 to 36 volt DC. So this means under engine cold crank conditions, the 12-volt battery dips to just about 9 volts, but still the device would be operational. So it could be used for cold start testing as well. And now I would just quickly like to jump over to play a very short video which shows the UEI pack logger configuration software and how easy it is to set the device up.
Hi, we're here to introduce the UEI Pack Logger. This comes with a web-based configuration and data display utility, which allows you to quickly go in and select the I/O board you'd like to use, enable a certain number of channels for different types of measurements, might be voltage, differential, with a specified gain. You can set your scan rate, then indicate how a particular channel may be triggered. You can trigger each channel independently. Then you can actually go in and check the status of what's being acquired. If you elect to have this user interface up, you're not obligated to have it showing. There's many ways to start collection. You can run continuously or use a trigger. You may want a certain number of scans before the trigger or a certain number of scans after the trigger. And that's what we have set up here. Now that the data has been recorded, we can download the data. It's actually in binary format, and it gets converted to ASCII CSV format on the fly. We do have a zoomable graph display, so you can zoom on the x-axis, as well as on the y-axis. The UEI Pack Logger supports a variety of different sensor inputs. Please contact us to discuss your particular application requirements.
So let's move on to the presentation. So while we are on this topic, I would also bring an application example where the UEI cubes were deployed as an InVehicle Logger. So we had this requirement for implementing a health and usage monitoring system for a hybrid bus engine. So the basic requirement was there was CAN data coming from the engine itself, and then a hybrid propulsion control system, and a battery optimization subsystem, and an air conditioning unit. And also there was serial data coming out of a door control system. So we use the UEI Cube to actually acquire these data. And also we implemented GSM communication for communicating if there is any faults in the vehicle. So there will be live communication from the vehicle to the control center to inform if there is any faults. And also these acquired data, we also implemented Wi-Fi transfer, so that when the bus reaches the depot at the end of the day, the data that is acquired through the day would be transferred automatically to the control system. And from there, the log data would be directly fed into the fleet health monitoring systems to do some maintenance checks. So the data logging and signal definition for these devices are very easy because of the availability of the configuration software. So this is kind of a real-life example to show that the application of these devices for an in-vehicle logging unit. So not just for fleet management, these devices are perfectly suitable for use in test development, where you would need to have data acquisition devices mounted inside a test vehicle during the ECU development process. So that's basically the three applications. So finally, I would like to also touch on the deployment options for these hardware before we go and take our final set of questions. So as I mentioned earlier, there are different deployment options that these devices could work in. There are two main modes here. So one is the hosted mode or the tethered mode. So in this hosted mode, these devices would just act as a slave device connected to an Ethernet network, and the application software would be running on a host PC. So we support a wide variety of operating systems. So you could use Windows, Linux, VxWorks, QNX. So the options are flexible to make whatever is suitable for your application. And also we provide API to actually interact with this hardware, and we provide different software bindings that you could use different programming languages for. So like C++, Python, Visual Studio, .NET frameworks. And also applications like LabVIEW and MATLAB, we provide integration with those applications, so it makes things easier if you prefer using those applications for your for developing your software. On the other side, we have the standalone or embedded mode. So this is where the application software actually runs on the unit itself. So you wouldn't need a host PC to actually run the application. So you could just compile the application into an executable, load it onto the hardware, the CPU of the UEI hardware, and you could just run there, and you can collect the data on the onboard either SD card or SSD device, which is built internally. So you have a couple of programming options for these ones. So you can have C++ programming, or we have Symlink integration, so you can build your application as Symlink models. And we are also adding in the process of adding Python support for this. And also we have a number of deployment options. As we saw earlier, we support EtherCAT, but apart from EtherCAT, we also support other protocols like Vistas, IDDS, OPC UA, Modbus, and many more. So that kind of wraps up the content for today's webinar. So I will have a quick look at to see if we have any further questions that has come in. So the first question is, do you support hardware for fault insertion in HEL? Yeah, so we have a 3-to-1 multiplexer boards, which you could use to switch between fault signals and simulated signals. So this way, so you can switch between your simulated signal, or you can insert faults by switching to the other input. So do you have any hardware solutions for battery testing applications? Yeah, so we have recently introduced a digital multimeter board. So this provides a 6.5 digit multimeter interface that can be used for measuring DC, AC/DC voltages, currents, and resistance measurement. So the number of inputs can be extended by using a MUX interface, which goes along with the DMM board. So basically, from a single multimeter board, you can have up to 132 wire or around 65 4-wire channels. So do you have any IP-rated hardware available for use in vehicle testing for mounting under the bonnet or wheel arch? So apart from the mill-style chassis, we are also working on a future product called the DNA brick. These devices would be sealed to at least IP67, and these are compact chassis which can house 4 I/O slots in there. And so this would be ideal for applications like that. So where you would be required to mount the unit under the bonnet or under a wheel arch. And I believe the product would be available by the end of this year. So is Automotive Ethernet supported? As of now, we don't have support for Automotive Ethernet yet. But yeah, so we would be happy to see if this is of requirement, and we would be more than happy to investigate that further. So I guess that's all the questions that's come in. I don't see any more questions. So if that's everything, thank you for joining in today. I hope you have a nice day, and I will pass the control over to Bob to give the closing down comments.
Right. Thank you, Prabhu. Hold on. Let me see if I can grab this. Okay, a few bits of housekeeping before we conclude today's presentation. Our next masterclass will be August 6th, and the topic for this particular webinar will focus on the analog output applications and solutions. Because we record every webinar and post the videos online, we have over a dozen now, which you can watch anytime on our YouTube page or on our own webpage. That's ueidac.com/videos. And finally, if you've got questions, need additional support, or you've got suggestions for a future webinar topic, please email us at support@ueidaq.com or give us a call, 508-921-4600. We hope you found today's webinar useful, and we will see you again in August. Once again, thank you for joining us, and everyone, please stay healthy.